So now we will discuss the different defects. Defects means where there are different types of defects, three of them: stoichiometry, non-stoichiometric and impurities. Okay, so stoichiometric defects, the two most important ones are Scotty and Frengel, and non-stoichiometric is metal excess and metal deficient defects. Then you have the impurity. So the most important is stoichiometric defect, where you have the Schottky and the Frengel defects. So for stoichiometric defect, it means that, for take the example of, let me change the pen, wait. Yes, for example, you take NaCl. So you have, that is Na plus and Cl minus ions, right? So 1:1 ratio, 1:1 ratio, and if this is the lattice, okay, lattice, consider this to be the lattice. If this is the lattice, stoichiometric defect means there will be vacancies. I'll take one chlorine and one sodium anywhere, okay? The lattice is going to be very large, so any two. So one chlorine, one sodium I take. So one positive ion and one negative ion I took. So now also again, number of sodium ions 2, number of chlorine ions 2. So 1:1 is the ratio again. So there is no stoichiometric change. That is called that is why we called it stoichiometric defect. Now there are two types, that is the Schottky and the Frengel defect. Schottky defect it arises because if some of the atoms and ions are missing from their normal lattice sites. So example, in the case of sodium chloride and potassium chloride, and it is seen in high coordinated numbered compounds, okay, and ions must be of similar size, that is size of cation should be similar to size of anion. Now what about Frengel? Frengel defect is found in ionic crystals, okay, ionic crystals, and size of anion should be greater than the size of cation, okay, and it arises when cations or anions leave their normal lattice sites and they occupy the interstitial sites, and here the density does not change, but in Schottky defects density changes. And in Frengel defects, it's observed in ionic compounds with low coordination numbers, okay. With this, we have come to the end of the chapter. We only have a very small portion left, that is the Bragg's equation. And yeah, non-stoichiometric defect is like, for example, ferric oxide, okay, ferric oxide, it will be 0.95 oxygen, okay. That means a certain amount of iron I have taken, but the amount of oxygen remains the same. Some ions of iron I have taken, but not of oxygen. That is by 0.95. Otherwise it will be 100%. 5% of it I have taken. That is what non-stoichiometric defect means. Means there is a change in stoichiometry. Okay. And then we have two types: metal excess and metal deficient. Metal excess means number of cations will be greater than the number of anion, and metal deficient mean number of anions will be greater than the number of cations. That's it. You need not probe further into it, because majority of the questions come from Schottky defect and Frengel defects. Then what we have left is the Bragg's equation. Bragg's equation. Let me change the pen. It's always the menace. Yeah. Bragg's equation. Bragg's equation. Okay. So crystals are studied through X-ray crystallography to understand their structure. So from using theoretical as well as what can we say, through as I said, crystallography, you get an equation D equal to n lambda by 2 sin theta. So n is the order usually 1 or 2, and d is the distance between two layers, like one layer over here and the second layer over here, no? So something like this, layer of atoms in lattice. So that distance is called the d, and theta is the angle at which the X-ray is scattered. So this is the only thing that you have to study from this part, Bragg's equation. Okay, so with this we have revised the complete chapter. Hope you all enjoyed it, hope you all understood it. If you have any doubts, please post your doubts in the comment section. Also check out my other videos whose link is in the description.